Right now, as we speak, theoretical physicists are literally losing sleep over a single number. Seriously, have you ever wondered why our universe exists in the exact, highly precise way that allows us to, well, be here? Today, we're diving into a cosmic explainer that explores a mystery so deep it challenges the very foundation of reality and is sparking a desperate hunt for new physics.
We are talking about a 1, followed by a mind-bending 120 zeros, 10 to the power of 120. Now, what's wild about this incomprehensible number is that it represents the magnitude by which the absolute most brilliant minds in science missed the mark on a fundamental feature of our reality. When theoretical physicists tried to calculate the energy of empty space, they were off by this astronomical factor. And because of that, we're looking at what is widely considered the absolute worst prediction in the history of physics. I mean, we have these highly successful, incredibly accurate models, right? Quantum field theory, general relativity, yet when they come together to predict the fundamental energy driving our universe, they fail spectacularly. So why is this absolutely crucial number so incredibly wrong? Well, answering that question might just require us to fundamentally rewrite our entire understanding of existence itself.
So let's get into it. Part 1. The worst prediction ever. To really understand this monumental error, we have to start with the forces that govern the very fabric of space-time. You see, the universe isn't just an empty stage. The space between galaxies is highly dynamic and it's stretching. Using the established principles of quantum field theory, scientists attempted to predict the energy density of the vacuum of space. Their mathematical models returned an astounding 10 to the power of 45 joules per cubic meter. I mean, that is literally off the charts. But when you look at astronomical observations, the actual number is about 10 to the negative 9 joules per cubic meter. That is up to 10 to the 120 times smaller. It's an error so incredibly vast, it's honestly hard for the human brain to even process.
Which brings us to part 2, unmasking dark energy.
Okay, so what exactly is this energy scientists were trying to measure in the first place? And why is it acting so strangely? Well, we call this mysterious phenomenon dark energy. Einstein showed us that space can stretch and warp, right? And in general relativity, it's not just mass but energy and pressure that influence the dynamics of space-time. Dark energy possesses a really bizarre property, negative pressure. Imagine a giant, cosmic, stretched spring gently pushing the universe apart. It basically acts like anti-gravity, accelerating the stretching of space on the largest scales of the universe and pushing massive galaxy clusters away from each other.
Now, think about normal matter for a second. As the history of the universe plays out, ordinary matter and radiation dilute. Space expands, so the matter within it naturally spreads out. But dark energy? It's completely different. Its density remains roughly constant over billions and billions of years. So while matter dilutes, this dark energy vacuum just maintains its weird negative pressure, slowly and very gently ripping the cosmos wider, causing the whole expansion to accelerate.
And here's where things get really messy. This mechanism is currently causing a massive crisis in cosmology known as the Hubble tension. Different, super-advanced observatories are getting completely conflicting measurements of this expansion rate, what we call the Hubble constant. Early universe models predict a rate around 67 kilometers per second per megaparsec, but direct measurements in our local, late universe using incredible telescopes like Keck and Hubble, they favor a faster rate of around 73. And just adding to the intrigue, recent independent data from the James Webb Space Telescope and gravitational wave observatories like LIGO are landing right smack in the middle, around 70 to 71. This deep tension is a huge red flag hinting that we might be missing a massive piece of the physics puzzle governing dark energy.
All right, moving on to part 3, the fine-tuning paradox.
Let's look past the current measurement tension for a moment and go back to that original, terrible prediction. What if that initial, massively huge prediction of 10 to the 45 joules per cubic meter had actually been correct? Well, if dark energy was a massive positive 10 to the 45, it would have immediately halted the formation of early galaxies. Stars would be pushed apart way more powerfully than gravity could ever pull them together. We'd literally just be left with a giant dark void with absolutely no structures or life. On the flip side, if it were a negative 10 to the 45, the universe would have rapidly collapsed right back in on itself in a violent big crunch. But instead, it is precisely hovering at 10 to the negative 9. If dark energy were off by even a fraction of a hair from this tiny specific observed value, you and I would simply not exist.
And that terrifying reality brings us to a really profound idea from physicist Steven Weinberg, who back in 1987 suggested that our universe's uniquely perfect dark energy value might just be a massive case of survivor's bias. This is known as the anthropic principle. Essentially, he argued that if a universe hasn't rolled the exact, perfect mathematical dice required to produce humans, well, there would be no humans around to observe it anyway. We only see this highly improbable universe because it's literally the only one capable of supporting us.
Now, Weinberg didn't just sit back and philosophize about this. He actually did the math. He calculated that for early, ancient galaxies to form just a billion years after the Big Bang, the dark energy density had to be smaller than 10 to the negative 7 joules per cubic meter. Because, by the time galaxies form, you've likely crossed the threshold for life to eventually form too. And, astoundingly, his calculated threshold perfectly correlates with the 10 to the negative 9 value we actually observe in nature today. It turns out, life and dark energy density are surprisingly interlinked.
So how do we explain this luck? Let's dive into part 4, the multiverse solution. Because if our existence really relies on such a mathematically absurd coincidence, we have to ask, how did we get so incredibly lucky? To understand the odds of this cosmic balancing act, imagine a giant cosmic slot machine. You have to generate 3 random numbers between -1 and 1, add them all up, and hope this sum perfectly cancels out to a magnitude of at most 0.00 with 55 zeros before the 1. That is the exact level of fine-tuning required for the various contributions of dark energy density to cancel out to a value compatible with life. When you put it like that, it sounds completely mathematically impossible.
The sheer persistence required is just baffling. It would take roughly 10 to the 56 attempts to get that perfect cancellation on our cosmic slot machine. But, and this is a big but, if you have enough tries, right? If you have a vast enough number of universes being created, that unlikely cancellation turns from a mathematical impossibility into an absolute inevitability.
And that leads us to the 2 leading multiverse theories that try to explain our incredible luck. First, you have the sequential multiverse, which suggests an eternally repeating process of big bangs and big crunches, with completely new physical rules and dark energy values arising each and every time. Under this theory, we just happen to live in the lucky iteration. Alternatively, you have the spatial multiverse, which proposes infinite realms of space forever separated from us, each with totally random dark energy values. In this scenario, we simply reside in a rare, life-friendly bubble floating in an infinite sea of dead, sterile universes.
But we aren't just guessing here. Part 5, Testing the Cosmic Mystery.
I mean, the multiverse is a completely mind-bending and perhaps slightly comforting concept that solves this fine-tuning problem without invoking intelligent design. But as of today, scientists aren't just sitting around philosophizing. They are actively hunting for hard empirical data to test our cosmological models. Humanity's absolute most advanced observatories are on the case right now. JWST is piercing through cosmic dust to measure the expansion rate with unprecedented clarity. The upcoming Roman Space Telescope is going to map clusters of galaxies over time and space to directly test the effect of dark energy on them. And the Veris C. Rubin Observatory? It will soon provide an ultra-high-definition time-lapse of billions of galaxies, offering crucial clues into exactly how dark energy influences cosmic evolution. They are fiercely hoping to resolve the Hubble tension and finally figure out if our physics models are just fundamentally broken.
So, as these incredible telescopes peer deeper and deeper into the dark, and physicists try to untangle the worst prediction in history, we are left with a pretty haunting question. Are the laws of physics a unique masterpiece, or are we really just one tiny, lucky bubble in an infinite sea of multiverses? The hunt for the truth is on. Thank you so much for joining this explainer, and stay curious.